then share. Okay. At first, I was confused why you got this wrong, because that's what I would have picked. But I think I figured it out. It's saying, like this, this picture is a little bit stretched out, like those coils aren't exactly touching. And what would happen if we shrank it a little bit? The thing that I wasn't, I didn't read correctly the first time was that there are the same number of loops and the same current. So one thing that was in my mind when I thought of a solenoid was this equation. No, that's not right. Where was my equation? So the equation I had was B equals mu little n I. I knew that off the top of my head as like the equation for a solenoid, where n, what I was interpreting n was, I thought n was the number of loops, but it's not. This little n would be, why isn't it here? That's usually a pretty standard thing.
Oh, it's actually the number of loops per length, I guess.
Right, yeah, so I was thinking it was this thing. So if that was staying the same, but so it's a weirdly worded question. If we knew that little n was staying the same and the spring was being pushed closer together, B would be the same. There's the same amount of current, n, the little n is staying the same, and mu, that's a constant. So then B would be the same. But what is happening is that capital N is staying the same and L is changing. So this is what we would get from using Ampere's law, which is like the, we'll get to it soon. It's, where is it? Right here. No, that's Faraday's law. Where's Ampere's law? It would be like yeah, this one. It's a circle. So you draw like some kind of path like that, where it's like a dotted line, and you talk about how much flux is going through that. It's just like Gauss's law, but for magnetic fields. And instead of an area for Gauss's law, you do for instance, this one would be a circumference. So if you were to evaluate that side, it would be 2 pi b. And then that's why this 2 pi ends up on the bottom, because they're taking it over here. And then I is just I enclosed, like Q enclosed from Gauss's law. Anyway, so that's how they get this equation. And then they just cancel the L's and they get this. So what we're doing in, if we, where is it? If we read this in a certain way, we are keeping big N the same, keeping I the same. That's always the same, but we're decreasing this thing. So if we decrease the length, then by this formula, B would increase.
So I actually had like 3 tries for this question. And I think I first did decrease, and then I did same. And I did same again because I was like, no, it has to be same. So maybe it was increase. Okay. Now that makes sense.
Oh, okay. So you don't have access to do it again?
Yeah, it was on the exam, so.
Oh, okay. I'm pretty sure that's correct. I think I was just reading it incorrectly. I just assumed that little n in that equation I knew forever was the number of loops, but that's a ratio. It's n over L.
So the answer would be the field would increase, or the answer would be the field would briefly increase to settle to the original value.
Yeah, I don't know anything about that. I don't think that's
that doesn't make sense, right?
Yeah, it doesn't make sense. There's nothing in these equations, especially because unlike this equation where the magnetic field would vary with time. So you see that little T right there. Here, there's nothing that tells us anything would change with time. So this is what's called magnetostatics. It's kind of like electrostatics. And then once you start doing stuff like this is called electrodynamics, where it's electric fields and magnetic fields depend on time, and they change. So yeah, I think it's just increase.
Gotcha. Okay.
And
Thank you so much. Actually, like, because he would repeat those questions, whichever I got wrong on the final two. Because like
nice.
that's what happened in 131.
Oh, cool. All right, cool. You'll be prepared. Okay, so I think we're good with Safari now. 222. Okay, so this is the big railgun thing. First step, I'll just repeat some of your work. Actually, let me drag this over here and then put that over there and put that here. Okay, that's better. Put that. Can I bring those over here? No. No. Okay. Don't know how to use my Mac. It's been 20 years. So, where's the other? Merge windows. Okay, that should be last. Oh, I'm the worst. Okay, put this in here. Put that in there. Oh, you're supposed to. Oh, whatever. Okay. This here. This there. Okay. Okay. What you did in the first one was you used the V equals IR because we have, let's see, where's the resistance? Yes, the bar that's being shot has a resistance. So you knew that the voltage applied was this, and so you did Ohm's law, rewritten the current, and got the correct current. And then you did the force, which is kind of like this. I don't remember what that's called. Actually, there should be a name for that. Lorentz force. And then you can rewrite this in another way. Instead of charge and velocity, you can do current and length. So you did that, and then because the length, I just assumed this, that the length, or the I'm sorry. So the length would be, where can I
It's 0.323.
Yeah, I was just going to draw an arrow because of this cross product, but apparently my computer's being annoying. Anyway, so right where my mouse would be, like the L vector right here, would be pointing in this direction, and the B, I just assumed it was pointing in the direction of the gun, like out this way. So if those two things are perpendicular to each other, we don't have to worry about the cross product, and we can just write them as a product. So it's sine of 90 degrees and sine of 90 is 1. And so you multiply all those things and you got the right answer. Then for acceleration, I just did F equals ma, and then I rearranged it kind of like this up here. So I had A equals the force over the mass. So the force we got from this equation, and then the mass I got from here.
Yeah, 1.97.
And then I got this thing. So I also did it over, where's the bottom of my screen? Can't find it. There it is. Yeah, so volts, got my current, got my length, magnetic field. I multiply all those to get the force. And then I have the mass, and I divide the force by the mass to get the acceleration, which is this thing. I don't know how many decimal points you usually do for the answers, but you know. Oh, that's right.
I usually try to keep them saved in my calculator because we might need it for later.
I already forgot that this was just an old exam. I forgot it wasn't, you weren't like redoing homework or something. So it doesn't really matter. Yeah. Okay. And then this one was the tricky one. This one you had to remember something from 131. So if you remember, like, it's mostly when you like shoot rockets and stuff like that. Like here, I'll just Google.
Yeah, projectile. No, that's the.
So these are like the four kind of, I guess there's five. It depends. Oh, that's silly. Yeah, there's four. Let's do it the same equation. But one of these we can use because what we want, if we reread the, God, I'm the worst. Reread the question, it says, what is the velocity when it leaves the rail? So that means that is VF, the final velocity. And so if we look at a few of these equations, we don't know the time over which the bar slides through the gun, so we can't use that one. There is no VF in this equation, but there is a VF in this equation, and we just found the acceleration. We know, I just assumed, that the bar is starting at rest. It's being shot out from, like, I mean, that's how most guns work, right? It's like it's a bullet in there, and it's not moving, and then you shoot it. So I assumed VI, the initial, is 0. But we do have delta x, because delta x is the distance over which the thing is being accelerated. So I just did 2 times the acceleration we found in the previous part times that distance. I got this thing in Excel, 96930. And then I took the square root of that to get because this is a squared right there. And so I found that it's leaving the gun at 311 meters per second, which, now that I think about it, I think that's a normal speed for like guns and stuff. Bullet speed, I can do railgun. Railguns actually exist. Bullet speed of railgun. Just to see if I'm in the right ballpark. Feet per second. Okay. I hope that doesn't mean meters per second. What did I get? Did I get 300? Yeah, that's really slow. Oh well. I'm pretty sure that's right. Maybe it wasn't a good idea to look up my. I mean, these are also military.
Also, the bar has a bigger area than a bullet. Maybe that's why our velocity is smaller.
Yes, thank you. That is a giant bullet.
Yeah.
Yeah, that's like a page, the bullet the size of a page. Okay, that makes me feel better. Okay, so I'm pretty sure that's how, considering these are right, I'm pretty sure the last two are right as well.
Yeah, I was actually, I got this equation, but I was doing something wrong with delta x value.
Oh, okay.
Most probably. Because I remember I was so confused what value to put for delta x. But now it's resolved. Okay, thank you so much.
Okay, what's going
on? Although they say it like x is equals to d, I don't know why I didn't focus.
But you did say this is from like one of your exams, right?
Yeah, I don't know how I missed that x equals d. Why didn't I put d?
Okay, what did I close? I closed 4.
This question, this next one is from a homework. It's not from an exam.
Got it. Okay. That there. Okay, this one was, I mean, I think this is a really cool problem because it uses, I think, one of the coolest equations from electricity and magnetism. This is one of Maxwell's laws, or Maxwell's equations. And it's really the one that kind of inspired Einstein to start thinking about the stuff on the next problem, which is like waves and like the particularly how fast magnetic fields go, and they always travel at the speed of light, which is a really weird phenomena of Maxwell's equations and electromagnetism. So if you actually look up the title of the first paper that Einstein wrote on special relativity, it doesn't say anything about special relativity. It's actually called like the electrodynamics of moving bodies or something. What's it called? Yeah, on the electrodynamics of moving bodies. And it's all about like the weird thought experiments that can happen when you start looking at light and how light moves and the difference between light and objects and all sorts of stuff. So that's like,
interesting.
Yeah, like when you like light, any light that's coming at you is just it's this picture right here. It's an electric field oscillating. So this is exactly this equation. So this says that the B field is like oscillating like a sine wave, and then there's much better pictures of this. I don't know why I keep trying to draw it. Wave. It propagates in one direction, and the magnetic field and the electric field are perpendicular to each other. So the wave, like the laser, is pointing in this direction, and all that light is E oscillating in this direction, and the magnetic field oscillating in the other direction. And so it doesn't, you can't, the only way you can make it travel slower is like if you were to shine it in glass versus air, like the index of refraction. That is something that can change how light travels through something. But other than that, it's like it's an invariant throughout nature, and that's kind of what made Einstein start thinking about how time moves and how space moves. And I think like 10 years after that, he actually did like the gravity stuff. So this is one of the coolest things that I remember from electricity and magnetism. Like the whole, your whole freshman year, you're working with these like epsilons and the mu's, and you're like, okay, the permeability and the permittivity of space or whatever. And it's actually, those two things are defined based on the speed of light, because the speed of like epsilon is all about like electric fields, and mu is all about magnetic fields, and how they interact with each other is at the speed of light. Let's see, where are they written?
I have a quick question. You showed me the diagram of that sinusoidal wave. Is there anything special about the points where electric field and magnetic field are overlapping?
I don't think so. I think what that is, that may be what's called like fringes.
Yeah, they create a dark fringe, I guess. I think. Maybe.
I think so. Yeah. So like constructive and destructive interference. This may be the answer. So for instance, if the two waves kind of line up on each other, then they do the superposition effect, which is that they add together to create an even bigger wave. Or if they're equal and opposite, so this one's up, this one's down, they add together to cancel out exactly. But I'm not sure if that's exactly, because this is kind of like waves in general. I'm not sure. That's a cool question. I don't know. I'm not sure. That's a really interesting question, but I can't answer it. I think it might have to do with that because I saw some other words about superposition and interference here, but I don't know if that's exactly right. Anyway, I'll get back to you on it. I know someone can answer it.
It's like something electromagnetic field coexistence create something else, like another branch or something. I don't know.
So these are Maxwell's equations. These are kind of, there are these two ways that you can view things. One of them is called the differential form, where this, like these little, these triangles are like this is the derivative or the divergence of E, the divergence of B, and this is the curl of E and the curl of B. Or what you can do is start to integrate things over, so for instance, in order to get from this equation to that equation, what you do is you integrate both of them over a given area. So I'm integrating this side of it over an area, and I'm integrating this side of it over an area. And what I do on the left-hand side is use something called Stoke's theorem, which says, well, it's basically, if I look it up, it'll just say that. It's basically that if you integrate something over an area, it's equal to yeah, it's I don't know the exact, like I can't prove it. It's just a theorem for math that we use, that the integral of the curl over a surface is the same thing as that integrating that just the vector field over a line integral. Let's see, is there something quick? No, that's way too advanced. I don't know how to do that. Bases. Anyway, it's something in math that we use a lot. Similarly, like we used it, we use something similar. It's called Gauss's theorem, divergence theorem. So these are two things that you use a lot in electromagnetism, that the flux over a closed surface is equal to the divergence. Let me see an example. I can't. Yes. So if you were to, where would you use this? Right here. So if you integrate this thing over volume, so this one you're integrating over area. So that's that ds. I don't know why they always use s. I guess it's for surface. Like this is surface, that's line, that's volume. Or area, distance, volume. That's always how I do it. Like this is a distance, that's an area, that's a volume. So here you're doing area, and this is where you use Stoke's theorem, that the integral of a curl is equal to the line integral, which is just integrating over a path. So for instance, here where I'm pulling out the b, the time derivative of b, in favor of just integrating an area element over the whole surface. So if you integrate an area element, it just equals a. So like the integral of dA is just a. And similarly over here, the integral, and because I'm using a circle for each of these based on the a circular coil. So the whatever, like in the last few sessions we did Gaussian surfaces. Now we can do Amperian loops or Amperian pillboxes, or I guess what would it be in this case? Because it's not Ampere's law. Faraday, I don't know, Faradian loop or whatever. But yeah, so we're integrating. I'm integrating over a loop, and the area of that loop is pi r squared. And here I'm doing a line, so it's the circumference of the circle. So the integral of the line element over the whole line is just the circumference of the circle. But just to, for completeness, I'll show you what Gauss's theorem means. Instead of over area, here I'm doing this side over a volume and this side over a volume. And what Gauss's theorem says is that if I integrate a divergence over a volume, I can instead do the surface area. This is usually negligible. In physics, usually the n is always pointing outward, and you usually don't have to worry about that. So for instance, this thing turns from the curl and the surface area to E. So that this one's Gauss's law uses Gauss's theorem, and Faraday's law uses Stoke's theorem. Okay. And then, okay, so a little bit more math here. I'm starting with this equation, which is kind of, you can say it in words as if a magnetic field changes over time, then it creates an electric field. Another way, like the reverse way to say it would be if you have a charge, which obviously creates a magnetic or an electric field, if you start moving the charge, you create a magnetic field. So it's like time changing magnetic fields create an electric field, and then moving charges create magnetic fields. And we can, let's see. So this one would be that the time moving, I'm sorry, the time dependent B fields. So if there's, if at one instant the B is this, at another instant it's that, it creates an electric field. Similarly, actually we can, this term right here, you probably won't end up using. You see right here, it's called with Maxwell's addition. If I just do the basic one, it is, because that was something that was added much later. So here, yeah, here it is. This is like the one that was around from like the 1800s. But then in the late 1800s, Maxwell saw that it wasn't like all these four equations weren't exactly consistent with each other unless you added that. But that's not really necessary for this problem or this discussion. But this J is current density or current. We can just call it current for the moment. And so current is moving charges. So this is, in words, this equation says, if you move charges, which are like, I think of charge, electric field. If you start moving the charges, which was unlike we did at the beginning of the semester where it was just a charge here, a charge there, what are the electric fields interacting with each other? If you start moving the charges, then you create a magnetic field. So that's like the relationship between E and B. If it's dependent on time, you create an E, and if you start moving charges, you create a B. Okay, use Stoke's theorem. So we have the line integral of E, we have the time dependence of B in this area. Those two things are perpendicular based on the question. Magnetic field is perpendicular to the plane of the coil. And so I just pull this guy outside. There's no reason for me to care about the dot product anymore because sine of 90 is, no, sine of cosine of, Jesus, what's the dot product? I forget. I think it's cosine. Yes, cosine. And if, I hope cosine of 90 is 1. I don't think it is though.
I think it's -1.
Why is it here?
Ooh.
It's correctly. It's perpendicular to the plane of the coil. Yeah, so the B field would be like this. Coil would be like that. And then the area element. Oh, I'm sorry. I kind of breezed over it too much, actually. If you go back, when I said you don't really have to think about that in physics with the N, you do actually, because I just messed it up. So this N would be pointing up. So if the circle, circle unit vector. So coil would, oh, that's awful, come on. Yeah, this thing, see the N pointing up? Well, if the area, or if the, what does it say? If the magnetic field is perpendicular to the plane of the coil, it points in exactly the N direction, because the plane would be this, and if it's perpendicular to that, it's like pointing straight through it. So the angle between the N and B is just 0. So cosine of 0 is 1. So that's where I did that. Okay.
So we would like theta is the angle between a magnetic field and N, the normal, basically.
Yep, exactly. Okay. So and another way to write this more carefully would be how they wrote it over here, which is dot N ds.
Okay.
I was just sloppy, and I forgot how the dot product works. Okay, now we just do that thing where we integrate over an area, integrate over the line. We have a circumference and an area. And then I bring this over to the bottom and I cancel the pi's. I cancel one of the r's and I get, and I also noticed in the question that they're only asking me for the magnitude of the E field. So it doesn't matter if it's negative or positive. So I just start dropping that stuff. I drop the negative there. And I have that the electric field is the time derivative of the B field and the radius over 2. Then I start plugging stuff in, remembering how to do derivatives of trig functions. The derivative of cos is negative sine. The negatives don't really matter here because remember we're doing the magnitude, so this didn't really matter. Just the fact that cos and sine and cos. In this particular point, we have something inside there. So yeah, we have like a whatever that is, and the t. So if we're taking the derivative with respect to the time, we need to pull that thing out. It's like the, I forget what that's called, maybe the chain rule or something like that, where you pull this thing outside of there. So you do, this is like, yeah, let me show you. It's like you take the derivative of the function and then what's inside the function. Yeah, this thing. So we have f is our sine, and g of x is actually what's inside it. It's 3,770 times t. So to take the derivative of that, we take the derivative of sine and just forget about it. So that's the cosine with everything still on the inside. But then we also take the derivative of 3,770 times t, which is just, you just drop the t. Because if you're taking the derivative of that, it's just,
yeah,
the power of 1 goes to 0. Okay, then we have that. So this thing is just on the outside, right? Yeah, that's just some prefactor here. And then I'm taking it outside. That's the A out here. I'm keeping everything on the inside because that's the A that stays in there. And I'm carrying along this R over 2. Then I used Excel to evaluate those two things. It gives me 1.81. And I simplified this instead of writing the scientific notation to 3,000. And then I plugged in my radius, which was about 0.5 meter, I think. Yes. And then I started plugging in. So now I have, this is my formula, E. This is my formula for E at a various times. So you see there's still a time in there. So that's where the problem tells me I need to plug in 2 different times. For one of them, I plug in a super, super small time, a 1,000th of a second. And this is in radians. And so radians is the easier one to look up on Google, because if I just type in cos of 3.77, it tells me what it is in radians. You have to specify degrees with most things to get it in different things like that. So anyway, it gives me a negative, but remember the question's asking me for the magnitude, and so that doesn't matter. So I have that number there, and then, yeah, that thing. And then I multiply it by this, which is my 1.8 from before, these two prefactors, and my radius over 2. So I multiply all those three things together, and I get this. And then I multiply those together to get that it's about 0.8 volts per meter. And then, funny enough, with this next time, instead of 3.77 radians, I have 37.7 radians, and that is almost exactly equal to 1, very weirdly. I didn't understand. I did this for like 5 minutes. I was like, what, that's such a weird number, like 37.7. Like, how is that so close to 1? I was like going above and below. I was like, what the hell? But yeah, apparently it's insanely close to 1. So, you know, if you really wanted to keep those decimal places, you could, but I just said it was 1. And then I have that, which is my factor from before.
Yeah, but I tried these answers and they didn't work. It says that the
Really?
response differs from the correct answer by more than 10%.
Oh wait, did I forget to divide by? I didn't divide by 2, I think. Yep. Okay, this is not right. That needs to be divided by 2. And then multiply them together. So this thing is half. So I guess just divide everything by 2. Yeah, right. That would be that times that. Yeah, so this needs to be divided by 2. And then those two things. Okay, so try this number. Let me make it bigger. Yeah, try that number. I forgot that part. For some reason, I didn't divide by 2.
Yeah, that's correct.
Okay. Okay, and then the same thing here. Just divide, and then yeah, this would be your answer for the next one.
Yeah, it's good now.
Okay, cool. Okay, that was almost disappointing because that was the problem I liked the most. Let's see, what next? Waves. This is a tough one because for some reason, every textbook, website, whatever, gives, you can ignore this. This was me trying to figure out what units to write down here because like the equations that I use in my class, because I'm actually studying like the same material for my like PhD qualifying exams. And like, these are the equations that I was using, but it's not in right units. So like we use things called Gaussian units for some stupid reason. It's just an extra level of difficulty, I guess, than like standard units. But these are the ones that you use. The weird part is whenever these equations are given, sometimes they don't put this. I think they really should put this special symbol here. It's a bar over it, which means that this is the time averaged energy for a B field and the time averaged energy of an E field. The reason that's important is they, in deriving these two equations, it's already been taken into account that the B and the E field are like, they have this dependence, this sign dependence. And it's actually, that's why these 1/2s are here. Because, let me find it somewhere. I forget what textbook I was using, so I'll just Google it. Energy density electromagnetic waves. Let's see if anyone actually writes it out explicitly. Because if you look on most places, they just they give it to you, like they give you those two equations, and don't explain where the 1/2 comes from, or this might be it. So that's the assumption. We're assuming that E and B are both waves that look like that. The sign of the cos doesn't matter. No, they don't give it either. Oh, here it is, kind of. Yes, okay. So that 1/2 actually comes from the fact that you're averaging over a given time. So if you average either the cosine or the the cos or the sine over a half or over an entire period, it actually equals 1. Yeah, so both of those two things together equal 1. And so because each of them carry the same probability, it's 1/2. Let me get a better math answer for you. Time average of sine squared. Let's see, what's this? Load. Okay. That doesn't help me at all. This is the best way that I always.
Yeah, that's an identity, right?
Yeah, so this is the whatever that thing is, that identity, and then because both of those things are just shifted by 90 degrees, the average of both of those things over the exact same full period must be the same, because they like if you look up sine and cosine, they cover the exact same area over a full period. So for instance, if you just shifted this thing by 90 degrees or pi over 2, they would be the exact same function. And so if you take both of them over an exact period, they both cover the same area. And so that magnitude of the sine squared and the cosine squared must be the exact same. And so if you're adding two things that must be the same and they equal 1, they're both 1/2. So that's where that comes from. But they really never explain that to you when they give you that energy density formula. Let's see if there was a better. Yeah, just read. I'm just trying to figure out how to explain where this equation comes from to you. Like, how is it related to that? Like an inductor.
It's correct. Oh my God. Okay. Something else.
Okay, it's kind of the solenoid. Okay. Energy stored in a solenoid is the inductance and the current squared. This is kind of similar to like 1/2. There's a really cool thing I talk about in the lab course where like springs are very similar to like circuits and how they go through things. So this equation is actually almost identical to like 1/2 kx squared when you talk about like springs. We know the self-inductance. You can get that from Ampere's law. That's again we saw earlier. We can get that from Ampere's law. If we okay, so they're saying the self-inductance of the solenoid, if you replace, or if you, so mu n I, and you replace that here. So what they're doing is they're taking the known expressions for B and L and writing W in terms of this. And then, let's see, if work, the energy stored. Oh, I'm sorry, that's not voltage, that's volume. And then energy density is, whenever you hear the word density, it's just the actual quantity, energy, and then it's over.
Divided by volume.
Yeah, or whatever that is. Okay, so that makes a little bit more sense. At least I know where that, like this equation comes from. You can get it kind of from a solenoid, where the work comes from, like this is like the inductance is kind of like your spring constant, I is like your displacement, x. This one, I think I did that in solenoid. That from earlier. The magnetic flux through each turn is that. Why is it? Oh, duh. That's just he wrote out Ampere's law without actually writing it out. He's yeah, so he just wrote that thing out for the flux because that quantity, where is it? Right there is also called the flux. Wait, no, that's not right.
It's the Faraday's law. It's flux. Yep. Field into area is the flux.
Mm-hmm. Okay, so the flux is B A, and then he's plugging in B here. The total flux, okay, so that's just one loop. That's just one loop. And then the flux through all of the loops is this guy. And then the self-inductance. What does that represent? I forget what that is physically. It is the tendency to oppose change in current. So that's kind of why it's like a spring. It's like if you stretch a spring, it wants to go back to itself. If you compress a spring, it wants to go back to its original position. That's why that analogy makes sense. The inductance is kind of like just something that resists change. It's kind of similar to Lenz's law, where like if you take a magnetic field configuration like a little magnet over like some magnetic metal or something, and you move the magnet, or changing the magnetic field, the metal will like create a magnetic field to keep it. It wants to stay. It's kind of like inertia, but like for magnetic fields and stuff. Okay, so that's where that comes from. He was using that to get this guy. Okay, so anyway, this is the equation for the energy density, time averaged. So when it says time averaged, we can actually completely, where is it? Oh no, we're already on this equation. We can completely forget about the sign here. So it's already taken into account that the sign has been squared and averaged over time by that 1/2. And so what we'll see in a second, so if you plug everything, I think, did I just do this on Excel? I guess I didn't write it down. So I did the magnetic field, which really the only thing that matters is this prefactor here. So 2.5 e to the negative 10. And then I Googled this, I always forget which one it is, either the permittivity or the permeability. I don't remember.
Yeah, 8.85 into e negative 12.
No, I think this is, yeah, that's epsilon. We don't want that one.
Oh, 4 pi into 10 raised to power negative 7.
Permeability. Yes, this is the one we want, mu. Okay, so it's 1.26 e to the negative 6th. Yeah, so here I'm just doing 1/2, where'd the equation go? Yeah, 1/2 b squared, squared over the permeability. And then I get, oops, do that. I get 2.49 times 10 to the negative 14th for the magnetic field. And tricky enough, the answer to B is identical. The reason for that is based on this like propagation thing. So these two things are traveling at the speed of light. One of them, you can see this kind of cross product here, but because they are perpendicular, I can just write them as a product. That's just a unit vector, so it's just 1, and I can write it like this. And then I have this kind of neat formula relating the electric field, or the magnitude of it, I should say. The magnitude of E and the magnitude of B is C times B. And this was that one thing we saw earlier, the relationship between C and E, or C and all these constants we've been using for years and didn't know what they were about. And so if I plug this whole thing into that equation I had for E, so if I plug in E, this substitution I have right here, then I'm squaring the square root stuff, and I get an epsilon and a mu, and the epsilons cancel, and I end up with the exact same equation I had before. So there's no need to try to like, oh, what's the electric field? Like, I was only given the B. How do I get the E for this one? You don't need to, because it's whatever the energy density for the B field is, it's identical to the E field. So if you're given B, you can find both of them, or if you're given E, you can find both of them, vice versa.
Okay, can I exceed? Okay, -14. For some reason, it's showing that it differs from the correct answer by more than 100%.
100%.
Maybe because there could be something related to sine kx minus the omega t. That's part of the magnetic field equation.
I don't think so. Make a math mistake again. Let's see. That's right. That's right. Yeah, I put it in super specifically. That, I don't know, maybe that's wrong. I don't know, let's see. Equals that squared. And then equals this thing over 2 times that thing. Should be the same exact, okay. Differs by 100%. Definitely not. Maybe, I know what I'll do. This is from the cat's book. So what if I think I have it downloaded somewhere. Let's see, what does cats say? It's not here. Let's get to that. Okay, got downloaded again. Illegally, of course. That's why I didn't download it. It's enormous. I can't think of any other formula for the energy density, though. I mean, that's kind of a well-established one. It's everywhere. Well, let me wait till this downloads. Oh my God, why is it doing
For average, maybe that's the keyword that maybe alters the formula a bit.
I mean, the average is just convincing me more and more that we should use the 1/2. That's what the average mean. Come on. Yeah. This takes. I think it's just my computer is like dying with Zoom and trying to download something at the same time. Yeah, I definitely don't want to wait for that. Oh wait, there we go. Okay, I don't know why it's taking so long. Whatever. I guess let's try some things. Maybe, I mean, it wouldn't differ by 100% if I left out that 1/2. Or we'll put it. This is 100%.
I was actually confused about this problem because my friend said that I have to divide it by 1/4 to get the correct answer. Like we have to multiply it by 1/4 instead of 1/2. I didn't understand the logic, but I tried dividing this answer by 2 and it worked.
So maybe I was wrong. And let me go back to that article we were having before, because that one was actually the only good one that did it. Energy density, electromagnetic waves. This one. So because you say divide by 4, that implies that this isn't taking into account the sign, and that when you do the squared, you need to do the sign again. So then you do the 1/2, which would be a 1/4. I didn't know that. Let's see. No, this wasn't it. Yeah, this one? Yes, I think this was it. Yes. Okay. Help me. Anyway, okay, so I guess I was mistaken. That 1/2 doesn't take into account the sign already. And what you need to do is utilize that, the time average of the time average of sine squared is 1/2, and then you use it with this equation. So this is a super general equation. I didn't know that. I thought the 1/2 was already taking into account the assumption that B and E are like sine and cosine functions. Okay, so that's wrong.
We are dividing, we are doing 1/4 instead of 1/2 because this particular magnetic field has a sign in it, and when we square the sign,
Yeah.
and a time average, it's equal to 1/2. Okay.
Yep.
Complicated. All right. Thank you so much.
Yeah, absolutely. Is there anything else?
There's just one question. If I would stick, he would be posting it sometime tomorrow. Like it's kind of a question that might be on the exam with a similar pattern. But if I find it a little bit difficult, I will email you. Okay. Thank you.
Cool. Yeah, I mean, you can see this is what I was working on before we started. It's all the same stuff, just a little bit. This annoying textbook Jackson right here.
Okay. Good luck with that. And thank you so much.
Yeah,
I'm
totally.
so nervous about this final exam.
So, I mean, didn't you get like a A+ on the last class?
Yeah, but like on the last midterm, I messed up. I didn't get a good grade. So